Hey guys, this video is going to be a little bit different than the usual videos because I am also using it for the fact that I have a sub today. So bear with me, I'm going to go a little bit slower than I usually do, and since we're using it for class, guys, if you need to, raise your hand, tell whoever's covering for me to pause it. Rewind, go back and see something again if you need to. Okay? Alright, so triplets seem to run in the Tribbiani family. Great-Grandma Tribbiani is one of a set of triplets. She had triplets, and each of them had triplets. The sequence shows the number of descendants in the Tribbiani family over several generations if this trend continues. Describe the sequence. That means, are we talking about arithmetic or geometric? Okay, write down which one you think it is. Okay, hopefully you said this was a geometric sequence. And therefore it has a common ratio of 3. Okay, write an explicit formula to represent this sequence. Okay, so G sub n equals our first term times our r to the n minus 1 power. Now, if you don't remember if you don't have memorized your explicit formulas and your recursive formulas and stuff yet, don't forget you have a cheat sheet. Okay, here's your cheat sheet. Don't forget that you have this. Okay, you can use that for your explicit formulas for arithmetic and geometric. Don't forget that you have that. Okay, so let's figure out the first 10 terms of the sequence. So term 1 was 1, term 2 was 3, term 3 was 9, term 4 was 27. And then we're going to continue filling in that chart. So term 5, term 6, term 7, term 8, term 9, term 10. Okay, so continue filling this in. Your calculator can actually help you fill this in a little more. Okay, you can watch this. Alright, I know my next term is going to be 27 times 3. Whoops. So if I type in, I already did it once, 27 times 3. Okay, that's not a big revelation, right? You knew you could do that on the calculator and type in, or, write in 81. Okay, that's not huge. It's probably also not a surprise that I could just click times 3 again, and I see ANS times 3, and I get 243. Okay, well that's not that exciting, Mrs. Andrews. Okay, but I don't have to type anything anymore except the enter key. Okay, now if I hit enter, it does the times 3 again for me, 729. In fact, I could hit enter like, what we need, 3 more values. Okay, 1, 2, 3. Okay, and we've got the next 3 values done. I just got to copy them in. 729, 2187, 6,561, 19,683. That's a little shortcut there for you. Okay. Now we're going to go to graphing. They set up the graph for you. So I've got 1 and 1. Well, 1 and 1 is, considering this is 0 to 2000, that's not exceptionally big. Okay, so here's 1. You're going to do it pretty much almost on the line. 2 and 3, gosh, not much better. Pretty close to the line. 3 and 9. 4 and 27. Mrs. Andrews, why on earth does this count up to 18,000? Well, our final point's going to be 19,683. See how these numbers started small, but then quickly blew up. So these first several values are going to pretty much rest right on top of the x-axis. When you're counting 0 to 2,000, there's not a heck of a lot of difference between 1, 3, or 9, or 27 for that matter. So 4 and 27. 5 and 81. 6 and 243. 7 and 729. Well, now we're starting to get a little bit bigger. So here's 1,000. Each box is 1,000. So 729 would be there. Okay, we're starting to get something we can reasonably graph. 8, 21, 87. A little over 2,000. 9, 65, 61. And 10, 19,683. 18,000, 19,000, all the way up here. Okay, and I'll take those. Okay. And not connect them. And think about why we would not connect those dots. Describe the shape of the graph. Okay. Well, the shape of the graph, if I connected the dots, would be a curve. Okay. And it is a curve. So it is exponential. How does the graph shape confirm your answer to part A? Well, things that are multiplying every time. Things that multiply. Grow larger, faster and faster. Is the graph discrete or continuous? Explain your reasoning. Think about it. Think about why would we not connect the dots? It's discrete. Okay, why is it discrete? You cannot have partial people. Also, the number sequences do not contain, I should say include instead. Values in between. So what I mean by that is if we go and look at our term value, 13927, if if I were to make dots that included, if I were to connect the dots, then a value like 10, which is a whole number, it's not a partial people, but a value like 10 would have to be included. But 10 is not in the number sequence. These numbers are the only numbers that can be in the number sequence. So I cannot connecting the dots, because connecting the dots represents that all numbers in between these values also count. So I cannot do that. Use the explicit formula from Part B to predict the number of descendants in the Tribbiani family in 20 generations. So that would mean n equals 20. So our explicit formula was g sub n equals g sub 1 times 3 to the 20 minus 1 power. And remember, don't do this part in your head. It's fine if you type it into the calculator already subtracted, but write it down that way because it's reinforcing the structure of the formula. So 1 times 3. I will also concede that putting the 1 there doesn't really change the outcome, but it's again reinforcing the structure of the formula. Now you can type 20, take away 1 here, or you could type in the 19 instead. You'll get the same answer either way. Big number. Okay, 20 generations in, we're going to get a huge number. Got to see what I'm writing, where I'm writing. Okay, here we go. Equals 1,162,261,467. That seems huge, but that's what geometric and by extension exponential functions do. They grow very large, very fast. Okay, so what you're expected to do in your homework, and this is the first one that's done for you in the homework, is use the formula that they give you. Okay, so remember that the first term you get from the first thing after the equal sign, the 15. Okay, then it says plus 3. So to get my subsequent terms, I'm adding 3 plus 3. So 15 plus 18, or plus 3 is 18. 18 plus 3 is 21, and so on and so on and so on down the table. Then you're going to take this table and graph it. Make sure you are labeling things like the axes with words and numbers that make sense. Okay, most of the time your x-axis is going to be 1. I hate that they leave off the 10 on the end. 1 to 10. The y-axis, you're going to have to count by numbers that make sense and get as high as you need them to. For example, I need to get at least as high as 42. My rule of thumb is you can count by 1s, 2s, 3s, 4s, or 5s, but after 5, you need to count by something that would be a money amount, a coin or paper money amount. That's a good rule of thumb. I do not want to see counting by 17s. Nobody does that. Okay? If you look at any publication or on the internet or in the news, that's not how you do graphs. Don't count by weird things. Okay? Let's do one more. An actual homework problem. Okay, term number. Remember, in an explicit formula, 3 would be my first term. So I'm going to put a 3 here. Then the explicit formula is telling me that each time I'm going to multiply. Oh, I wanted to do a different color though. Multiply by 2. So 3 times 2 is 6, times 2 is 12, times 2 is 24, 48, 96, 192, 384. Then I start having to slow down and I can't do them in my head as fast. 8, 16, 768. And then I'm just going to go for sake of time. 768 times 2. Ah, I didn't do it. $1,536. Okay, now I gotta graph this stuff. Zero, 1, 2, 3, 4, 5, 6, 8, 9, 10. Those are our term numbers. Okay, now for the y-axis, our value of term, I got to at least make it to 1,536. I've got 10 squares to play with, so I'm probably going to have to count by 200s to make it. And again, in the beginning, guys, these curve-shaped graphs that are geometric, they don't look, the first few points are difficult to graph because they're such small numbers compared to the scale of the y. You're basically drawing little dots just resting on the x-axis for the first few. So 1 and 3, I mean, how high up is 3 compared to the whole thing being 200? Not very high at all. Okay, 6. Still not very high. I mean, almost no different to the eye for 3 than 6. 12. 24. Okay. Halfway would be 100, right? We're still at 48. 6 is 96. That's close to 100. That's close to halfway. 7, 192. We're finally making it almost to the top of the first line. 8, 384. Now we're getting pretty big though. 9, 768. And 10, 1,536. Do not connect the dots. Okay, so what kind of graph do geometric sequences make? They make exponential, and if I go back and look at number 1, that was the example one done for you. That makes a linear. Arithmetic makes linear graph. Ah. You should now be able to work on this homework assignment for the rest of this period. See how much of it you can get done so on Halloween night you don't have homework. Okay? Have a good day. See you tomorrow.